So today we are done discussing new material on SQL and relational algebra. So yes, this is a SQL class, but there's some theory in it as well, and I was asked to keep the theory. So had I dumped the theory, things would have been maybe a little bit more relaxed, but I don't really know what can actually be reduced in this class and still have it be, a comprehensive SQL class. So so I'm looking at a couple of things. So we're not done with theory yet, but we're done with learning new SQL and relational algebra. We'll still see some SQL this class, but I'm not going to test on it. I'm going to test more on conceptual things. So we've talked about schemas. We started with that back in lecture 1. And normalization is the process of refactoring a set of tables so that we minimize redundancy. So redundancy sometimes creeps into tables. And we want to minimize redundancy across our schema. And the way that we do that is by using a concept called normalization. Normalization basically takes your schema, splits it into different subrelations, and such that when you rejoin those subrelations, you get back the original relation. But the subrelations themselves separate concerns, but also eliminate redundancy. So what I'll write here is that normalization is not just about separation of concerns, but that is a lot of it. There's other stuff that goes with it. There's redundancy and a few things we'll talk about today. So when we do have redundancy in a table, we decompose the table into 2 or more tables with a common join key. And this lets us remove that redundancy. But how do we actually do that? We'll learn about that today. So it reduces redundancy in tables. It also separates concerns in a database like we've talked about, but it also prevents, so this is new today, data integrity issues on insert, update, and delete because of these redundancies. And finally, we reduce copies of data. The more copies of data we have, the more likely we are to corrupt the data or to change it in some way that breaks referential or data integrity. Now, typically in a table, we want to query over just a small number of columns, not like 5 million of them. So normalizing lets us do this, have a small number of columns to query over instead of a larger set. So going back, so what's old is new again, going back to this YouTube table, this is almost normalized. We have separation of concerns here. We have a video table that represents video concerns, ID, title, channel, and another table called comment that addresses comment concerns, what video the comment was on, the comment text, and so on and so forth. Now, we also noted that there was a bit of a problem here, and that's these set of columns here. These are a form of redundancy, not one that we're going to talk about today, but I do want to call it out. These are called generated columns. Basically, it keeps track of the number of likes. Anytime somebody hits like, something happens in the database. It depends on what database it is, but essentially it'll increment that count, and that count is stored and updated in the database. This isn't great practice, but there are use cases for this. So this is basically generated column redundancy, and that's not really what we're talking about this lecture, but I want to call it out. Now, if we ignore those columns, is the YouTube video table, does it have redundancy in it still? I'm switching color, so it must. What redundancy is still in this table aside from the generated columns? What?
Comment likes.
The video table.
Oh, sorry.
Mm-hmm.
The title and video ID both, I don't know, the title could be redundant here.
Well, each video has a title associated with it. There may be duplicated titles, but each video does only have one title associated with it, so we need to keep that. What else? The channel ID, or the channel name, I should say. This is redundant. What we should have is a table called channel that contains an ID and the name of the channel. I'm repeating for every video the name of the channel, which is redundant and, waste space. So we want to get rid of that. So that's the process of normalization. Now, as you can see, I looked at the data and I just figured out what's redundant in the table. We can do that. That's the intuition I want you to build, but there's another more principled way to do it. Yeah.
If we get rid of the channel column, we'll have to introduce the channel ID column in the table.
Yeah, so here we would have channel ID instead.
So how how does that help us in terms of?
A string uses a lot more bytes than an integer does. So a 32-bit integer, and I should know this, I believe is 4 bytes. A channel name is the number of bytes times the number of characters. So we save a lot more space by using IDs. So we only store the channel ID in the video table. Now what about the comment table? Is there any redundancy there, excluding the comment likes and replies? No, there's no redundancy there. That's pretty good. Now we could decompose this into 2 tables. Video ID, comment ID, comment text. That's what's called over-normalized though. Now we have to join tables together just to figure out the text associated with each comment. Because the comment text is essential to the comment ID. So we don't want to over-normalize here. Sometimes people get carried away. They say, everything's redundant. Just normalize everything. Put every column in a different table. And that's over-normalized. So if we take the natural join is okay now again, because we're talking about theory. Between YouTube video and YouTube comment, we get back a relation called YouTube that contains information about videos and comments in the same table. This is called a denormalized table. For every video, each video is going to be repeated, and its information is going to be repeated for each comment. It's denormalized. So our YouTube table is going to look like the following. I'm going to have a video ID still. That's the common key between the two. But now I'm also going to have the video data in here, as well as the video ID, and also the comment data as well as the video ID, all in the same table. 2 concerns shoved into 1 table. This causes some problems. Redundancy, obviously, that I just said. But more importantly, data integrity issues on update, insert, and delete, and also a delay in creating new records. What do I mean by that? Oops, delete. What I mean is that if we keep this denormalized table, YouTube, and we add a new video to YouTube using this table, what am I going to put for the comment area? I put in the data associated with the video, but then the comment section is going to be all null, presumably. Now I have to keep track when I see a video. Have I seen this video before? If I haven't, well then insert it, but then put nulls for all the comments, for all the comment data. If I have seen it before though, and this is the first comment on the video, so that's the second thing I need to keep track of. I search for the video and update the nulls to the data associated with the first comment. The third thing I need to keep track of is, if this isn't the first time I've seen this comment on this video, I now add a new row with all the video information repeated and the comment information repeated. So I have 3 things the database needs to do now in order to insert a new video. This is very, very problematic. That's one thing I could do. The other thing I could do is I could delay the entry. I could say, okay, I've created a new video. I'm not going to write it to the table yet because I don't want nulls. So I wait for the first comment to arrive. It's stored in RAM. Once the first comment arrives, I then write the row into the table. Now for every successive comment, I write full rows into the table. But I gotta keep that friggin' row in RAM. What if a comment never arrives? It's a video where comments are disabled. It's gonna be in RAM and I never write the row. The logic here is very complicated on how I handle an insert. So that's what I mean by delaying updates. So that's one reason why denormalized tables are bad. Now before, when I first started programming, pick 10A as a math major, intro C++, I tried doing this kind of thing. I didn't know anything about normalization or databases. You run into it very, very fast. You're like, what, gosh, so much to keep track of. Well, that is programming for you, but it's a little bit too much to keep track of. So the normalized table allows us to separate these concerns and quickly insert data. So a new video arrives, just add a new row to the video table. A new comment arrives, just add a new row to the comment table. None of this other messy stuff. But there's a couple other things to keep into consideration too. In your notes, this is one, so I do this all the time in my other class, the CS class. I haven't done it as much in this class. I sometimes upload a student slide deck, and then I have a master slide deck I post afterwards. Sometimes I like to do exercises that wake people up. In this case, I just didn't want to create a slide, and I didn't want to just give you this and then not know what the hell it meant. So here it is. You can take notes or you can read it after I post the slides. This basically is exhibiting a update insert anomaly. So suppose I have two relations here, subrelations, R1 and R2. And R1, for analogy, we'll call video, and R2 we'll call comment. And instead, I decide that I want to use the denormalized table. I want to use R, which is the natural join between these two subrelations. And it looks like this. So again, as I just talked about, what is the update anomaly? The update anomaly is, let's say I want to change alpha in this denormalized table to a sigma. I have to do this in multiple places. I have to iterate through this whole table, which is inefficient, and I have to replace every alpha with a sigma. Here I did it twice, big deal. But in a big table, I'm gonna have to do it many, many times. And that's inefficient. We need to remember, whoever's programming this, to make multiple changes. So that's the update, that is the update anomaly, is that we have to make that change in multiple places. Whereas with the normalized table, I make the change once in R1. That's it. So going back to that, all I do is I make the change once. And if I want to reconstruct R to get two sigmas, I just join R1 and R2 together. I don't have to make multiple changes. So that's one example of an anomaly that can happen with a denormalized table. The other one is the insert anomaly. So this one I actually already talked about. What do you do with a row? Do you put nulls in? Do you wait? This is also an insert. These are both cases of an insert anomaly. By the way, I am going to post this, obviously. So the full deck will be posted. We're also going to talk about the final and some parting words. I never include that in the student deck because I want people to hear it from me first rather than read it. Then once you've heard it from me, then I post the updated slides that contain everything. And obviously it's in the recording as well. All right, is there a delete? There's also a delete anomaly. Very similar to the update anomaly. If I decide I want to delete the alpha row in R, I have to make sure I delete it everywhere in R. Whereas with the normalized schema, R1 and R2, I only delete it once in R1. And if I want to get back R, I just join the two tables together. So are there any questions about these phenomena and why denormalized tables are bad in general? Is it crystal clear? Awesome. Okay, NoSQL does not work this way. There is no concept of normalization in NoSQL. This is strictly a relational thing. Okay, now, there's some of you are advanced. Are there cases where normalized tables are good? The answer is yes, but can you tell me why? When would they be good?
When you need all information in one row.
When you need all the information in one row, good. Can we generalize it a little bit?
In cases where joins might be inefficient or slow.
Yeah, so these are both similar answers. Can we generalize that more? It's very, very close. So an implementation is a data warehouse. Most of you, if you work at a big company, are going to be using data warehouses, not actually databases, but they both use SQL. So that's why you're here, usually. In OLTP, joins are ad hoc. So RDBMS, which is a relational database management system, is OLTP, meaning online transaction processing. It basically means that reads and writes are random. A system or an app or a person will write data and read data at all times of the day. It's random access. Joins are ad hoc. This means we decide that we need data all in one row. We write a join, and then we throw the join away probably, and then maybe we write it again the next week. But we're constantly writing these different joins to solve different problems, and then throwing them away. This is very expensive, so joins are very expensive. And what I mean by that is expensive in multiple ways. They exhaust RAM, especially if you don't write the join correctly. They take time to process. We had one case where configuration changed and somebody ran a query that crashed the server. This configuration change and the query were different students, so nobody's really to blame. But what happened is this person ran out of RAM because their recursive SQL query just kept running, or it may have been a left out or join, I can't remember. It was a cross join. It kept running, we ran out of RAM. When that happens, the operating system starts swapping to disk. So it starts taking the contents of RAM and writing it to the disk. Now, even though the disk is an SSD, which is pretty fast, it's slower than RAM, and it's slower than not making this mistake. So once we started writing to disk, it still wouldn't finish. It exhausted the disk, and we ran out of disk space. There was not much on there to begin with, and it crashed the server. So that's expensive. Disk space and RAM are very expensive, especially on the cloud. And then also, right, that was my main point. Disk space and RAM is very expensive, especially on the cloud. Expensive as in money. So, ad hoc, we do ad hoc and OLTP, but in a data warehouse, what we do is we write a join once, read many. And by many, I mean hundreds, thousands, millions of times. So you have some data you want to join together. You join that data together overnight, and then you just read from that joined table over and over again. Here, this is a little bit inefficient in a database sense, but in the data warehouse, this is perfectly fine. And this is where a lot of you are going to get your data to write reports. You'll work with a data engineer or a dashboard. You'll work with a data engineer to write that join and materialize it in a data warehouse. So that now you're executing a query, like a select star almost, against join data, which is very fast. So if you're not going to just join ad hoc, you instead need to do this join frequently. Use the data warehouse. Now, this at UCLA, you see this all the time. There's, your student information is spread across multiple tables. And when you read your study list, or when I look at the roster of students, that's a join between several different tables. Your identity with your major, with your enrollment, basically. We don't join, every time I click on that button, we're not joining the tables together. That would be extremely expensive. Typically, every day, maybe even every hour, I believe data is only updated once an hour in this regard, we get an updated roster. So it's done through presumably a data warehouse. So it's very fast to do. Speaking of that note, the way that these systems used to work, my UCLA in particular, was it didn't, now the system calls a bunch of APIs to get data and do what it's going to do. Back in the day, it used to use screen scraping. So there would be a script that's written in JCL or some mainframe language by IBM, and it would load the terminal screen with a bunch of text, enter in the codes to get to the right screen, scrape the text on the screen, and then reformat it into a web page. They did that for way too long, but it's extremely slow. So joins are expensive. Join once, read many. Great. All right. Define redundancies in a schema. We look for a series of mathematical constraints, kind of like functions, called functional dependencies. So let's say I have a relation that contains attributes x and y. These are they're attributes or sets of attributes. They don't have to be individual attributes. We say that x functionally determines y, or x arrow y, if and only if each value of x is associated with exactly one value of y. So kind of like a function. So if I have x1 and it's associated with value y1 and y2, this means that x does not functionally determine y. That's not a function. I can have a case though where x1 and x2 both map to y1. That's okay. It doesn't mean x functionally determines y, but it means that it doesn't not mean that. And I don't remember if surjective, injective, onto are one-to-one. These definitely aren't one-to-one. I don't believe they're onto either. So functional dependencies. For each, in plain English, for each x, there is exactly one y. And that's it. Whoops. And then strike through the whole slide. Exactly one y. So that's basically what we're going to play with today. Now our break is usually at 5:30, 540. Okay, cool. Another way that we can state this theoretically is the following. If x to y holds on R, then for all pair of tuples T1 and T2 in the relation, it must be true that x associated with tuple 1 is equal to y associated with tuple 1. And that any two on these two tuples, any two y's must be equal when the x's are equal, essentially. Essentially, it says the same thing as what I just said on the previous slide. So x to y, x arrow y, means x functionally determines y. There's a variety of other ways to say this. X defines y. X determines y. X identifies y. X maps to y. X implies y. Now be careful with implies. We're not talking about double implication here. Just implies one way. And finally 2, x to y. You'll hear me say all of these. They all mean the same thing. I use these when I get functionally sick of saying functionally determines. That wasn't funny. All right. My last class enjoyed that more. I'm getting so functionally sick of saying functionally determines. I set it up wrong. So when a functional dependency exists, it typically means that we have redundancy and that we can split the relation into two subrelations. One containing x and y, so both sides of the functional dependency, and one containing x, which is a join key, and everything else but y. What on earth does that mean? So, here it's written in math, but let me draw it up on the screen here. So we have x, let's say we have x, y, z, a. That's my R. And let's say I have x functionally determines y. I can divide this little relation into two. One called R1 that contains x and y. So basically a mapping, which has a key of x. And R2, actually, this doesn't have to be a key in R, but it's a key in R1. And R2 is going to contain x. It doesn't include y, because that's in the other one, z and a, with x being the key. Now, if I want to get back R, I just natural join R1 and R2 together. Now, we should be able to do this. If I natural join R1 and R2 together, I should be able to recover R perfectly. I should not get any more rows than I had in R, and I shouldn't get any fewer rows than I had in R when I join these two together. This is called, if my next slide is ordered properly, okay, it's not. All right, so this is called the lossless property that we'll get to in a moment. Now, isn't this just intuitive and more or less context specific? Yes, but there are going to be times when you don't have the intuition for the data that you're working with, and you need to be able to still remove redundancy or somehow plan out a schema. And so these functional dependencies can help you do that. Now, the theory behind this is more critical for DBAs, database administrators, and data engineers. So for example, Frank, who teaches 405, at least I think he still teaches it, is a DBA, I believe. And he knows all about this and presumably either understands it really well or uses it, one of the two. So you need to know a little bit about it, but we're not going to go nearly in depth with it as I do with my CS class. We get very tricky with it there. We don't need to do it here. So in practice, the lossless join property means that if I join together the two subrelations, I should recover R, exactly R. It also implies that the cardinality of the set, or the number of rows, should be equal to the original relation because they contain the exact same data. So people sometimes incorrectly think that lossy means that we just have fewer rows, we have data loss. If we have more data, that's also lossy. So when we talk about things like image compression, like JPEGs or and whatnot, that uses a compression methodology that is somewhat lossy, but it doesn't only lose data, meaning it loses some details of the image. It also inserts data via a statistical process called resampling. And adding that data is also lossy. It wasn't in the original image. So lossy means both here. So let's look at a couple of examples here. Let's say I have this little table R that contains information about cameras, the model name, the category or brand, and the price. I also have I decompose this into two subrelations. One that contains the model name and the brand is associated with, and one that contains the brand and the price. And I try to join R1 and R2 together. What happens? Well, the join key in the natural join is the common attribute, so it's category. I'm going to join these two rows together and these two rows together. So my output has 2 rows. Then I'm going to join these 2 rows together. So now I have 3 rows in my output. And then finally, I join canon with the first row and the last row again. So now I have a total of 5 rows. So the cardinality of the join is 5 rows, but the cardinality of R is 3 rows. Does R1 bow tie R2 give us back the same result as R? No. So is it lossy or lossless? It's lossy. It's very lossy. So again, the join has to give you back exactly R, but also the cardinality has to be the same. If they're exactly the same, that implies the cardinalities are the same as well. Now what about this one, this little Greek letter example? Now the keys here are B. That's the only common attribute between the two in the natural join. I join these 2 rows together and these 2 rows together. So my output is going to contain 2 rows, and R contains 2 rows, and the rows are identical to R. Remember that also the order doesn't matter in a relation, it's a set. So even if you got a different order of tuples, we would still say that the decomposition is lossless. So is this lossless or lossy? It's lossless. We don't gain or lose any rows, and the rows are exactly the same. Are there any questions about losslessness? All joins should be lossless, and all the joins we talk about in this class for today are lossless. Okay. Oh, fun little example. So we have this table. I kind of already showed this, but I'll do it again for good value. I have this table that contains x, y, a, and b. I know that x functionally determines y. Let's actually change this. Let's say x, y functionally determines b instead. So I'm going to have one relation that contains what attributes? Just shout it out. It's okay if you're wrong. X, Y, and B. Good. And what is R2 going to be? X, Y, and A. Good. So X, Y, and B is going to be alpha, beta, pi, delta. And this one's going to be, oh, and I'm missing one, gamma, eta, delta. And this one's going to be, well, just X, Y, and A. So alpha, beta, gamma, eta, and A, which is sigma, gamma, and pi. Cool.
XY does not functionally determine B because it has different values.
Oh, you're right. I just said, let's just assume that. Let's delete that. I said, let's assume that. I didn't want to do another simple one. Let's assume XY functionally determines B, and then write what the decomposition would be. You're absolutely right. Let's just get rid of this, so it doesn't confuse anybody who reads this afterwards. Yeah, great eye. XY does not functionally determine B here. So I guess to be complete, I'll write out I'll write it out. R1 is going to contain XY, but no duplicate. So alpha, beta, gamma, eta, and then R2 is going to contain X, A, and B, which is going to contain alpha, sigma, pi, alpha, beta, delta, and gamma, eta, delta. Any questions or errors here? That should be correct. Okay. If there are no questions, we'll move on. Now, functional dependencies are similar to superkeys and candidate keys in that it depends, how you solve it depends on how I ask the question. I could ask you to construct the functional dependencies only in the instance that I give you, so the 4 rows that I give you, or however many rows I give you, or based on the context of the problem. Number 1 is easier for you as a student to answer. You're given 4 rows with Greek letters, solve the problem. Number 2 is a little bit harder, but it's more practical for what you're going to be doing in your career. So which one am I going to ask? I don't know, but we're going to do both. All right. Now, because this is math, there's a bunch of properties that we can use on these functional dependencies, and we're going to go through a few of them. So we're going to say that alpha, beta, and gamma are sets of attributes in some relation. The first axiom we have here is trivial, a trivial functional dependency. That looks like AB functionally determines A, or A functionally determines A. I am myself. If I know my DNA, I know my DNA. If I know my social security number, I know my social security number. It's reflexive, very trivial, doesn't give any information. AB to A, though, is also trivial. If I know somebody's UID and their name, I know their UID. If I know somebody's UID and name, I know their name. Again, trivial. So this means the right-hand side is contained in the left-hand side, basically. So as an example, UID functionally determines UID and major. Functionally determines UID. It also functionally determines major, but hopefully you can figure that out. The next one is augmentation. This basically says that given a functional dependency, I can throw the same attribute set on both sides, and it's still a valid functional dependency. So what does that mean in our little example here? If UID, let's drop the braces here, functionally determines name, then UID and major, which is extraneous, functionally determines name and major. Okay, we'll add them back. Transitivity, this one you should all be familiar with. If alpha functionally determines beta and beta functionally determines gamma, then alpha also functionally determines gamma. So let's use the dorm example again. Let's say your UID functionally determines your dorm number. I know you don't live in dorms, that's why I didn't want to use this example, but I like this better than my other example. And your dorm number, room number, functionally determines the room type. So it is a single, double, triple, whatever. This implies that your UID functionally determines your room type. Simple transitivity. Now these are called Armstrong's axioms, and they're always true. Are there any questions so far on these? Okay, now there's another one called union. This one we're actually going to write a mathematical proof for. I'm not going to ask you to do a proof on the exam, but I just want to show you that you approach this very similarly to math, because, well, it is. It actually comes from, relational algebra actually comes from I don't remember the branch it comes from abstract algebra, actually. I want to say it's like Galois theory or something like that, but I don't remember. So, if alpha functionally determines beta, and alpha functionally determines gamma, then alpha functionally determines both beta and gamma. Let's write a proof for this. I'm given that alpha functionally determines beta. We're going to call that statement A. And we're given that alpha functionally determines gamma, which we'll call B. The first step is I apply augmentation. With alpha to B. So that's going to give us alpha functionally determines alpha gamma, which is equal to alpha functionally determines alpha gamma. 2, I'm going to apply augmentation with alpha. With gamma, sorry. With gamma to A. So this gives me alpha gamma functionally determines beta gamma. Now you see what's going on here. I have alpha gamma on the right-hand side here and alpha gamma on the left-hand side here. What can I apply now? Transitivity, great. Apply transitivity. To 1 and 2. This implies that alpha, let's see, so given this, we get alpha functionally determines alpha gamma, functionally determines beta gamma, which is equivalent to alpha functionally determines beta gamma. QED, check mark, filled box, whatever, check. That's the end of the proof. So we can prove each of these. Are there any questions on this proof? I think there's another way to do it. Still you use augmentation, but there is a second way to do it. If there are no other questions, anybody still need this? Excuse me. No, we're good? All right, we'll move on. There's 3 more. These are a little rarer. We do use them. My other class where I try to be a little trickier, I even don't use these sometimes, especially the last one, pseudotransitivity, which is just plain weird. Composition. If alpha functionally determines beta and gamma functionally determines delta, then alpha, gamma together functionally determine beta, delta. So what does this mean? This means that if your passport ID or your social security number functionally determines your driver's license number, and your UID, so collision of 2 worlds here, functionally determines your major, then your passport ID and your UID functionally determine your driver's license number and your major. Hopefully not too groundbreaking, except for the context. Decomposition, as in tables. So we're going to do this a lot. If alpha functionally determines beta gamma, then alpha functionally determines beta, and alpha functionally determines gamma. So if UID functionally determines name and major, then UID functionally determines your name and functionally determines your major. Now there's a catch here. I'm surprised nobody brought up. We're assuming here that every student has exactly 1 major. If we didn't, these functional dependencies wouldn't hold. So that's decomposition. The last one is pseudotransitivity, which is weird. If alpha functionally determines beta and delta beta functionally determines gamma, then delta alpha functionally determines gamma. What the hell does that mean? Well, UID functionally determines major, and let's say the major and your class level functionally determines your advisor or your counselor. So all freshman CS majors have 1 advisor, all senior CS majors have a different advisor. What this means is that UID and level, because UID functionally determines major, this thing functionally determines advisor. So this is called pseudotransitivity. And yeah, we're going to use these a little bit. We're not going to go into a whole lot of detail about these, but they are useful for what we're going to talk about. Are there any questions? Okay. And if I need to slow down to write things, let me know too. Am I missing a page here? Oh, getting ahead of myself here. Suppose we have this relation. Is B to C satisfied? Does B functionally determine C? So we have B1 here is associated with C1. B2 is associated with C1. And B2 is also associated with C2. So does B functionally determine C? No. Because of this here. So B2, C1, so these guys here violate it. Now, does C functionally determine A? So we have C1 is associated with A1. C1 is associated with A1 again. C2 is associated with A2. But also C2 is associated with A3. This is a problem. So no. What about A functionally determines C? That is true. Here I have A1 is associated with C1. A1 is associated with C1 again. A2 is associated with C2. A2 is associated with C2 again. And A3 is associated with C2. Now this is okay. Remember, it's okay for two x's to map to the same y, but I can't have one x mapped to multiple y's. So yes, that one is satisfied. Okay. Exercise for you to practice for the exam, and I'll give you the answers here. What do you think actually I'll just give this to you because it'll take a while to figure this out. The candidate key here should be A and D. A, B, and A, D. Find out why. Now, one thing you can do, really the only thing you can do here, is go through all subsets of these four columns and see which ones are super keys, and then identify the candidate keys from that. Now, exercise 1, there are many first order functional dependencies, meaning one attribute to one attribute. Test all of them. So that's 4, choose 1. So there's 4 of those. We've already done 3 of them. No, it's not 4, choose 1. 4, choose 2. I don't remember, it's late. Anyway, there's a few of them. You need to test A to B, A to C, A to D, B to C, B to D, B to A, C to A, C to B, C to D, D to A, D to B, and D to C. However many those are, those are the ones you're going to check. Now, the only one you should get is D to B. Now, are there any functional dependencies of the form alpha to beta gamma? So 1 on the left, 2 on the right? No, there's not. Are there any where there's 2 on both sides? Yes, there's, I'm sorry, 2 on the left, 1 on the right. Yes, there's several. There's AB to C, AB to D, AB to CD by the union rule, AD to B, AD to C, and AD to BC. So as you can see here, AB determines everything. It determines C and D, and AD determines everything because it determines B and C. All 4 attributes are determined. So this tells you that the candidate keys are A, B, and AD. Okay, so to try to prove that to yourself, and then now we're going to move on to another example. Let's say I have this little table, and I'll explain this as not everybody's familiar with the system. A is the season, so the election year. B and C are the winners, so the president and the vice president. D is the party of both, because I don't think there's ever been a case in modern history where it's been different. And then the home states for both the president and the vice president. Now we have a couple of rules here that we can exploit. The first is we're going to assume that none of them have ever changed parties. Given that, well, let me first define something else. The key. The key is A. A determines everything else. Now, going back to 1, assume that none of them have ever changed parties. What functional dependency does this imply? B to D and C to D. Yep. 2, assume that a president can choose a different vice president for re-election. What does this not imply? Or which functional dependency does this imply does not exist? But B to C. So B does not functionally determine C. Some history, I don't remember if there's a case in history where the president chose a different vice president. There's a more recent one though, which was Donald Trump saying that he wouldn't choose Mike Pence to be his VP. So that would be one case that would adhere to this rule. But historically, I don't remember. I say that all these are realized in history, but I don't remember what that case was. So anyway, let's assume it's that one. And then 3, a vice president can serve multiple presidents. What functional dependency does not exist because of that?
C to B.
C to B does not exist. Now there's a couple other things. There's a couple other things that we can derive here as well. What does the key tell us? What functional dependency exists?
A to all the subsets.
A to everything. A to B, C, D, and E, and F. To me, intuitively, I'm going to say A to B, C. It is true, though, that A functionally determines B, C, D, and F. I could write all those out if I want, but that takes a long time. So A to B, C intuitively makes sense here. You have a season and you have 2 winners. What other functional dependencies do we have here? There's 2 others that are obvious. B to E and C to F. There's a ton more. There's a lot more. There's hundreds of thousands more which you can write by using Armstrong's axioms exponentially. Now, this gets to the question, how do we grade this on the final? Typically, I've been pretty lenient with this. Please don't list hundreds of functional dependencies. 8 is usually the max I will accept. Typically, what we'll then do is we'll make sure that you've covered all of the basis, the important ones. If you have some others that are implied by the basis ones, that's fine. But they all need to be correct, and all the important ones need to be there in order to get credit. There is a way to do this in a sane manner. It's called finding the minimal cover. Now, this is an example of either an NP complete or an NP problem, set cover and whatnot. But there is an algorithm we can use to reduce all those functional dependencies to one nice small set. And it goes like this. First, we take all functional dependencies that have a complex right side. So there's multiple attributes on the right side. Doesn't matter how many are on the left, just the right. And we use decomposition to list them all out. So we have AB to CD, we do AB to C and AB to D, both of those. This makes the set bigger, but we're going to shrink it in a moment. Second, we look at the functional dependencies that were created now, and all of them, and we cross out any that are inferred by any others. This reduces the set a little bit. Then finally, next we remove extraneous attributes. An extraneous attribute occurs when you have something like this. When you have 2 functional dependencies like this, and so you have AB to D, AC to D, and B functionally determines C. In AC to D, in AB to D, B is extraneous because we can determine C from B. So we really only need AC to D because B implies C already. So here in A, B to D, B is extraneous because it infers AC to D. Then we use the union rule to clean up. So if I have a bunch of like A to B, A to C, A to D, I now convert it to A to B, C, D. Now, I may have to start over and do this process iteratively, recursively, until the set doesn't change, typically is how we do it. But typically, 1-2 cycles is usually enough. So let's look at an example of how the minimal, or sometimes called canonical cover, works. Suppose I have these functional dependencies, A to BC, B to AC, and C to AB. The first step is use decomposition. This gives me A to B, A to C, B to A, B to C, C to A, and C to B. The next step is remove redundant FDs. There's a few redundant ones here. What's the first one that looks good to you? Let's actually copy this so we can use it. Which one's redundant here?
A to C
is redundant, so I get rid of it. It's redundant because I have A to B and B to C. So by transitivity, we can derive A to C. So A to C is gone.
B to A.
B to A. So B to A. We don't have a B anywhere. Oh, we do. We have B to C. Yeah, so B to A, gone. We have B to C and C to A. So by transitivity, we have B to A. There's one other one. C to B, gone. Because we have C to A and A to B, by transitivity, C to B is redundant. Now this all involves transitivity. It's possible to find redundant functional dependencies using pseudo-transitivity and all the other axioms we learned. I probably won't do that, but maybe I will, but it won't be that much more complicated than what we're doing here. Now, do we have any extraneous attributes? Do we have any functional dependencies that have two or more attributes on the left? No. So, not applicable. Finally, we apply the union rule to what we have left. Are there any attributes that have the common left-hand side? No. So our final set is A functionally determines B, B functionally determines C, and C functionally determines A. That's the minimal cover. So some of you, you're doing the problem and you end up with F up there, with that set. We then have to check that that is equivalent to our solution, which can be challenging. We've actually used software to do this before, where we've written a script to check each functional dependency to make sure it holds. Try not to do that, try to use this, but if you do, just limit it. Don't give us everything under the sun, like limit it to like 8 or something. That's usually reasonable. And so any questions? So this is just a trick to reduce a set of functional dependencies into something that's easier to grade. There is a second way, there's a second answer here, depending on which, there's a lot of transitivity here. There's another way to do this that's equally valid. So I'll let you figure that one out, but it's not necessarily unique. Okay, so we've talked about removing functional dependencies, or identifying functional dependencies. Now what we're going to talk about is normal forms. The normal forms help describe how much redundancy is removed, how much redundancy there is in a relation, and how much redundancy we've removed by decomposing a relation into subrelations. So if a relation is not in a good form, we can decompose into subrelations to get it into a better form. So for example, if our company requires BCNF and my table's in 3NF, I could decompose that table to get 2 subrelations or more that are in BCNF. There's 8 normal forms. We're only going to talk about 2 of them in depth. That's third normal form and BCNF, Boyce-Codd normal form. We need to quickly go through first and second normal forms so that we can understand third normal form. But there's 8 normal forms. There's also fourth normal form, which uses a multi-value dependency, which is similar to a functional dependency but more complex. There's fifth normal form, which is typically used in data warehousing. There's sixth normal form. There's also domain key normal form, elementary key normal form, and essential tuple normal form, which all kind of lie in between the various numbers here. We're only going to talk about 3NF and BCNF. So first normal form. Every table should be in first normal form. This one's a bit controversial though, because stuff's evolve in the data world. First normal form says that all data types must be flat and simple. There's no nesting and no collections. Now up until homework 3, this was true in this class. All of our types were atomic. Nesting is JSON. It's one example. And an array, which is also in your homework 3, is a collection. These mean, when you have these, you've violated first normal form. Typically when you have an array, you'll explode the row out into different, you'll explode the array into individual rows. We'll talk about that in a bit. There are no repeating groups. We'll get to that in a moment. But also there is a key there must be a key on the table, a primary key, for first normal form to hold, and there must be no null values. This is controversial. Actually, all of this is controversial. Because if you have nesting or collections or null values, automatically relational theory has died. But we still do it. And so first normal form is kind of hand-waved. We have a mnemonic for first, second, and third normal form. For first, all non-key attributes depend on a key. In other words, there exists a primary key, plus some other stuff. Okay, this little table is in first normal form if we assume that code and term are primary, the keys. I have atomic attributes, no nesting, no collections. I have no repeated groups, we'll get to that. And I have a key in the table and no null values. We're good. This is in at least first normal form. This is bad. In the codes column, I have an array. This is a non-atomic type. So not in first normal form. What I'd want to do is explode the array values into individual rows. So I'd have 18S Smallberg 201031, and then 18S Smallberg 201320, and so on and so forth. So multiple rows per professor. Here's where we talk about repeating groups. This is an example of a repeating group. I have 3 columns that impart a certain order, but it's a meaningless order. So meaningless order to the columns. It doesn't matter what's in code 1, code 2, or code 3. I could swap them. It doesn't matter. There's no semantic meaning behind these columns. That is the definition of a repeating column. Now, if I have, in like one example we did, UID, name, homework 1, homework 2, homework 3, do you think this is a repeating group? It's not a repeating group, no, because these 3 columns have a semantic meaning. Homework 1 presumably comes before homework 2, which comes before homework 3. There's a semantic meaning here. So not repeated. So because this example has a repeated group and it has nulls, it's not in first normal form. Mm-hmm.
So if a student didn't finish their homework 3 then, is it repeated?
I'm sorry?
So if a student didn't do their homework 3 then, it's going to be a null value.
Yeah, if you have a null value, so in the homework example, if you put a null value, then yes, it would not be in first normal form. We're going to assume everybody did the homework, which is the ideal case. Anything else? That's it for first normal form. To make a table in first normal form, add a primary key, remove any collections or non-atomic attributes, and remove nulls. We're going to assume in this class that every table is in at least first normal form. Second normal form. In order for a table to be in second normal form, it must be in first normal form and also adhere to a couple other things. For every attribute in the table, the attribute must be part of a key, or it must be determined by the entire key. No partial dependencies. Now, if a table's in second normal form, if we decompose it into second normal form, we're getting closer to separation of concerns. So, the mnemonic here, here's an implication. If a table is in first normal form and there are no composite candidate keys, it's automatically in second normal form. So think about that. The mnemonic states that each non-key attribute depends on the key, the whole key, no partial dependencies. Now, what does that mean? Let's look at this example. I have a table of student ID, course name, and instructor. What functional dependencies exist? First of all, what's the key? So the key is AB. So what functional dependency exists then, based on the key? AB functionally determines CD. What other functional dependencies exist here?
B gives C.
B to CD, yes. B to C or B to CD, yeah. Now, there's two ways to do this. We can either identify the functional dependencies or look at each attribute. So first I asked you to find the FD, so we did that, good. Now we look at each non-key attribute. The non-key attributes here are C and D because A and B are part of a key. C and D must be determined by the whole key. So C, it is determined by A and B because A, B is a key. But do we need A and B to determine C? No, we only need B. Relies only, well, needs only B. Let's put it that way. B is sufficient. That's called a partial dependency. Therefore, this table is not in second normal form. It's a partial dependency. So what do? We decompose it in order to make it into second normal form. I'm going to have one table that contains the key AB, and a second table that contains the functional dependency B to CD. The first table is a little meaningless. It's basically a study list mapping. But now these tables are in second normal form. So are there any questions on second normal form? Okay. Third normal form. This is where we start getting more important. There's two definitions of third normal form. They're both equivalent. For a table to be in third normal form, it has to be in second normal form. Any non-key attribute must depend only on the key, and must depend entirely on the key, and only on the key. There are some attributes sometimes that can be determined from the key and from other non-key attributes. That's not allowed in third normal form. So, for example, transitivity is not allowed here. No prime attribute can depend on any non-key attribute. So let's take a look at something like that. Let's first finish off the mnemonic. All non-key attributes depend on a key, the whole key, and nothing but the key, so help me God. A student added that last part, which is brilliant. So all non-key attributes depend on a key, the whole key, and nothing but the key. So let's look at this example. We have election winners again. What is the key for this table? In case you don't know how the system works, the election is not determined by number of votes that a candidate gets. It's determined state by state. So in each state, whoever wins the vote in that state wins that state and gets a certain number of electoral votes. So California is 55, smaller states it's like 2, and whoever gets the 270 first wins the election. It's based on electoral votes, not individual person votes. So based on that, AB, thank you. Make it easy, cut me off, shout it out. It's AB. The season and the state determine the winner for that state. Okay, so what does that mean? Well, we have one functional dependency right off the bat, AB to CD. Is there any other functional dependencies that hold here? C to D, yep. Now, let's use the attribute rule. The attribute rule states that all non-key attributes must be determined by the whole key and nothing but the key. So C, is C determined by the whole key? It is, because we need to know the season and the state in order to know who won that state and season. So C is determined only by the whole key. What about D? Is C only determined by the key? Well, it is in context. If you're thinking about the birthday, yeah, the birthday is unique here, but in context, that's not the case. Now, what about D? Is D determined by the key? It is, via transitivity. D is determined by C, which is determined by AB. So AB does functionally determine D. But does it depend only on the key? No, it depends on C. So if I know C, I can get to D. I don't need to know AB. So no, D depends on key and or C. So no, this table is not in third normal form using the attribute definition. Make sense? You guys are handling this a lot better than my undergrad class. It's always more confusing there. And there's some things that are the opposite. SQL is harder for you all, but easier for them. It's very fascinating to see. So it's not in third normal form. If I want to get this, if I want third normal form, I have to decompose. And I do that here. The first table represents A, B to C. The second table represents C to D. I no longer have transitivity here. If I want the transitivity or want to get back R, I just join the two tables on C. In the textbook, there's an algorithm called the synthesis algorithm that lets you decompose tables to your heart's content into third normal form. Intuition is better, but if you're like me on an exam, your intuition always feels faulty. And so having an algorithm can sometimes be easier for you. So if you want to use a synthesis algorithm, that's fine. Now there's a second, more theoretical take. The method that we just used here I call it the attribute method. There's a second method based on functional dependencies. What we do is we find all of our functional dependencies and we check each of these three conditions on each functional dependency. If any of them are true for each functional dependency, that functional dependency is good for that normal form. But if any of the functional dependencies fail all three conditions, that functional dependency violates that normal form and the relation is not in that normal form. So first we check, is the functional dependency trivial? In other words, is it of the form alpha to alpha or alpha beta to alpha, where the right-hand side is in the left-hand side? Is alpha, or the left-hand side, a superkey for R? And finally, is beta part of a candidate key? So is the right-hand side part of a candidate key? For each functional dependency, if any of these are true, that functional dependency is good. All we need to find, though, is one functional dependency that violates all three, and it's not in third normal form. So let's do that here. We have our functional dependencies AB to CD and C to D. Let's actually redo this so it's AB to C and AB to D. So we do a couple of checks. Let's do these checks down here. So we have trivial, super key, candidate key, check. AB to C, C to D, AB to D. All right. Is AB to C trivial? No. Is AB a super key? Yes, because AB is a candidate key. Is C part of a candidate key? No, but it doesn't matter. We've satisfied one of the conditions. So that functional dependency is good. Now we move to C to D, which we determined C to D violates third normal form. But let's do this anyway. Is C to D trivial? No. Is C a super key? No. Is D part of a candidate key? No, right? So C to D violates all three. C to D violates third normal form. Therefore, this relation is not in third normal form. These two definitions are identical and equivalent. Identical implies equivalent. This definition of third normal form is from this charming man named Carlo Zaniolo, who is one of the world's top database theory researchers. He retired in 2020. He actually used to teach 143 with me in a different quarter. And his entire class is relational algebra, I remember. So literally everything on the board was math and relational algebra. We did learn SQL, but that was kind of, just something we did along the way. It wasn't like a big goal in the class. The big goal was all of these relational algebra constructs. And if you knew relational algebra, well, SQL should be really easy, according to him. So what was funny about him is that he retired when the pandemic first started in the middle of winter quarter 2020. And I could just imagine what happened. So week 8, we all go remote. And I'd have to find a student to ask him if he just like stopped, if he just ended the quarter early. I mean, it's only 2 weeks. And he ain't returning. But anyway, go Bruins. He's really funny. Funny character. So third normal form is usually good enough. And it guarantees a couple of interesting properties. It satisfies losslessness. All the decompositions we talk about today satisfy losslessness. But it also satisfies something called dependency preservation. I'm not going to get into dependency preservation for this class, but basically what it means is that when we decompose a relation into subrelations, each subrelation realizes one of the functional dependencies. If we don't preserve dependencies in a decomposition, it means that in order to check that the dependency holds, we have to join two subrelations together, which is not ideal. So we're not going to worry too much about that for this class, but just kind of know what that is. Now, we could still have, third normal form is usually good enough, but we can still have a case where it's not good enough in one very nuanced situation. And that nuanced situation occurs when we have overlapping candidate keys. So let's say our candidate keys are AB and AC. Those candidate keys overlap on A. So we could potentially have a situation where we still get an anomaly with third normal form. So now we'll talk about Boyce-Codd normal form, or BCNF. It's sometimes called 3.5 normal form. This is my favorite one, and usually I recommend decomposing to BCNF if you can. The check is reduced to 2 steps instead of 3. We look at our functional dependencies, and we determine, is the functional dependency trivial? If it is, we move on to the next one. If it's not, we check whether or not the left-hand side is a superkey for R. If it is, great, we move on to the next functional dependency. If it's not, though, if both of these aren't true, that functional dependency violates BCNF, and the table is not in BCNF. Then in order to decompose, we have to decompose it to get subrelations that are in BCNF. So this is more strict than third normal form because we no longer have that third escape hatch, that third condition. So this is one of the only tables, or a table that looks like this, that violates BCNF but is 3NF. So instead of trying to figure this out, I'm just going to give you that the candidate keys here are AB and AC, and the functional dependencies here are AB to C and C to B. Now, let's check if these functional dependencies satisfy third normal form and Boyce-Codd normal form. So the first check is trivial. Second check is superkey. Third check is candidate key, which only applies to 3NF. Is AB to C trivial? No. Is AB a superkey for this table? Yes. So AB to C is okay for BC and Fness. Let's move on to C to B. Well, let's check candidate key for third normal form. So is C part of a candidate key? Yes, because AC is a candidate key. So AB to C is good for 3NF and BC and F. What about C to B? C to B is not trivial. Is C a superkey for R? No. So it is not BC and F because those are the only two checks. And then finally, is B contained in a candidate key? Yes. One of the three conditions holds for 3NF, but none of the conditions hold for BC and F. So this table is in 3NF, but not BC and F. How would I decompose it? Well, I take the violating functional dependency, which is C to D, split that out into its own table, and then split out everything else. So then I might have, I guess, A and B, potentially, in its own table. So 3NF, but not BC and F. Are there any questions on the test for BC and F? So Boyce-Codd normal form is a very strict normal form. Now, let's say, another way I can ask this question is, excuse me, I can give you a relation. You find the keys, you find the functional dependencies, and you figure out whether or not that table is in the normal form. That's one way to do it. Another way that's easier to test, but a little more complex, so I don't know which way I'll do yet, is I give you the relation, the attributes, and I give you the set of functional dependencies. And I ask you, is R and B C and F? Now, how the hell do I answer this question? Well, the first thing is I need to know if a functional dependency is trivial or if the left-hand side is a superkey. So what do I need to know here in order to answer this question? I need to know what the superkey is. So I need to find it. Now, something I left out of this class is the concept of a closure. One way I can find the superkey is I can take each attribute here, find the closure, which means I apply every functional dependency to that attribute, and I find out iteratively whether or not I can derive all the other attributes in the table. If I can, then A is a superkey for the table. We're not going to do that here, though. Here we're going to draw a picture. So if I give you a problem like this, it's going to have to be simple enough where you can draw a picture. I have A functionally determines B and C. So A, B, and C are somehow related. Next, C functionally determines B. Well, A, B, and C are kind of already in the same set, so I just draw a little arrow there. Then I have D and E. Well, D and E are disjunct from A, B, and C here. So A, B, and C are kind of in their own little island. And D and E, with A being a super key for A, B, and C. And then over here in DE land, I have D functionally determines E, and E functionally determines D. So, looking at these functional dependencies, let's look at the first one, A to BC. It's the left-hand side of superkey. First of all, what is the superkey?
AD.
AD is one superkey. What's the other one? A and E are the superkeys. If I know A and D, I know A, B, C, D, and E. I can derive them. If I know A and E, I can derive A, B, C, D, and E. So I have to have, both. One from each island, basically. Happy islands. So looking at the functional dependencies again, we have A functionally determines B and C. Does this schema satisfy B, C, and F? Yes or no? So A to BC, I check if it's trivial. It's not trivial. So the answer is no. And we violate it right on the first bat. A is not a superkey for R. Therefore, we found a violating of FD. This schema is not in BC and F. A to BC violates, and actually, all of them violate BC and F. So any questions? Okay. So bottom lines, and then we'll take a break. Right, so there's two ways I can ask the question. Given a relation with data, and you infer F, and then you check F or you check the attributes. Or I can give you a relation and a set of functional dependencies. Now, like with third normal form, BCNF guarantees lossless join. That's very, very important. I believe fifth normal form is the last normal form that supports losslessness. Fourth or fifth, I can't remember which. But it doesn't guarantee dependency preservation. So sometimes you'll decompose the BCNF. It's a valid decomposition, but in order to check whether or not a functional dependency holds in your subrelations, you're gonna have to join some of them together, which isn't ideal. So in a database system, if you have an assertion, you've coded an assertion based on a functional dependency, the only way to test it is to join two tables together, which is very inefficient. Now, in many cases, there are multiple ways to decompose into BCNF that are equally correct. Sometimes one of them doesn't preserve dependencies. Sometimes none of them preserve dependencies. Sometimes all of them do. It just depends. So it could be a complex problem, and it can involve recursively decomposing. Now, I didn't do an example here, so I can't remember if I tested on this last year. A decomposition. If I did, though, it would be very similar to what we did for third normal form and second normal form. BCNF removes all redundancy due to functional dependencies. Does it remove all redundancy? No. It only removes redundancy due to functional dependencies. If I had a multi-value dependency, which we won't talk about, BCNF isn't enough. I'd have to go to fourth normal form. If I have a generated column, BCNF is not going to be enough. I don't know what normal form we would need for there. So there may be redundancy due to other causes. So a functional dependency is just a constraint. It specifies a constraint in your database. When you design a schema, you should try to strive for BCNF. If not, third normal form is fine. You should strive for losslessness, and you should really strive for dependency preservation as well. If you can't get dependency preservation with BCNF, then use third normal form. Third normal form is usually acceptable in industry because most tables that are in third normal form, or most schemas that are also usually in BCNF. Now this is the part where you kill me. How is this related to SQL? It really isn't. There are no relational systems that are based solely on functional dependencies. They're based on relational algebra, but not functional dependencies. You can specify them in MySQL. So uniqueness, by specifying a unique or primary key, that's a functional dependency. You can also specify your own assertions. We didn't talk about that in this class, but it's in your textbook if you're curious. That's another functional dependency. But the system does not work in terms of functional dependency theory, basically. Now, this class, 402, is supposed to be an intro to SQL. It's supposed to be somewhat agnostic to what kind of system we use. So obviously we use MySQL here because you have another class that's going to use MySQL and other database systems. And typically that's how we teach SQL anyway. But SQL is extremely important for other things like data warehouses. Even R, you can use SQL. Python can use SQL a bit. So it has a lot of uses. Now where you're going next quarter is 405. So which I believe you do a little bit of dashboarding and or data warehousing. So I want to talk a little bit about that and differentiate it with what we talked about in terms of theory in this class. So let's go through to that. MySQL and other RDBMSs, so Oracle, DB2, Postgres, MySQL Server, are all what are called OLTP, or that's a technology, online transaction processing. It basically means that the system is designed for interactive use and more or less ad hoc querying where, let's see, where do I leave off here? Where the reads and writes in the system are random throughout the day. Typically, these systems are used in production. At a startup, you might use a database for everything, but for example, at a large company, for example, Facebook runs on MySQL, or at least it did when I was there. So all of the stuff that you do as users, those of you who still use Facebook, is being written into a MySQL database and is being read from a MySQL database. Now, people all over the world, at all different times of the day, are using this production server. So it has to be highly optimized for reads and writes at any given time. Now, that's different from what a lot of you are going to be doing in your career and your internships. Here with OLTP, each result and write is a result of some kind of transaction. So a select, an update, an insert, or a delete. So OLTP is optimized for quick reads and writes that are very frequent. And it strives to minimize redundancy because redundancy is a real performance killer in OLTP and relational databases. It's designed for production use. So the data is read and written by end users essentially. So the end user, for example, in the Facebook case, doesn't read what's in the table. They see what's on the screen, which is data that comes from a database in some fashion or form. But the end users are typically the ones that interact with the production database through some proxy, the proxy being, the web app. And it also abstracts data as a table, so a 2D representation with rows and columns. On the flip side, OLAP, or a data warehouse is the implementation, the system, and OLAP is a concept. OLAP is very different. OLAP is from the 1990s, that meme, it's the 90s, go for it. OLAP was very popular in the 90s. Some of it is still popular today, but it's evolved into what's called a data warehouse. It implements OLAP operators and schemas, but also adds a lot of other functionality that RDBMS and OLTP already have. So data warehouses have become a lot more flexible and a lot more useful and powerful over time. So another type of system, this OLAP or data warehouse, the user, there's two different users, the reader and the writer. The writer is typically a system. It's not a human inputting data. It's not a human inputting data via some proxy, via some web app. It's inserted by some job. In Linux, it's called usually cron, C-R-O-N. It's a scheduled job that runs at a certain time every day or every hour and pulls data from somewhere and puts it into a data warehouse. The readers, though, are typically you. It's you or an app. So it can be you, an app, or things like let's write this up. Oh, I should have done that later. Anyway, there's 3 use cases for OLAP. One is reporting. There's actually more than 3, but these are the big ones. Reporting is one. So some app reads the data in the data warehouse and produces a report for it. You, though, typically tell the app you want that report. Number 2 is dashboarding. Now, somewhere in this program, I need to at some point get a pamphlet or something that explains the required classes for this program. There is a dashboarding class. I think Song is teeing it, so I think it's this session. I don't know. But at some point, there's a Tableau dashboarding class. Are you taking that right now?
No, it's in the final.
It's the second year. Okay, I didn't realize there was a second year that you're gonna take classes, or at least that last quarter. Okay, so the last year you'll take a dashboarding class. That typically uses a data warehouse. Why? Because they're extremely fast and efficient at extracting data. Okay, so dashboarding is very important. You may or may not do that in your career. I haven't. I've developed one dashboard my entire career. It just depends on what kind of analyst you are or what kind of data scientist you are. The third use case is just pulling data, which sounds lame, but let me explain. If you're trying to create a classifier or something, the features for the classifier may be in a bunch of different tables in MySQL or Postgres, whatever. But if you put that data, you join that data together and load it into an OLAP or data warehouse system, what you can do is just read each observation and all the features associated with it directly from the data warehouse. Now these days, you may have heard of things called vector databases. Anybody heard of those? So vector databases are becoming hot. Basically, all they store are vectors of information. They're used for fast retrieval for large language models and things like that. Anyway, that you know, if you're doing machine learning, that may be your data warehouse. Anyway, where was I going with this? We can use data warehouses just to pull data very, very quickly because typically the data is aggregated for us already and it's also joined for us already. We don't have to write our own joins. Okay. OLAP stands for Online Analytical Processing. Okay, so they're not as common anymore, but the OLAP terminology and concepts are implemented in data warehouses. Now you're gonna work with these a lot. They work completely differently from OLTP. Most of your data in a large company is gonna come from a data warehouse, maybe not from a database. It just depends. So in RDBMS, data is conceptualized as a table, rows and columns. In OLAP, technically the data is represented as a cube. So with height, depth, and width. But when you access the data, it looks like a table still. So an OLAP cube looks like this. Let's say we have Amazon product sales data. One dimension of the data might be the shipping date, that's the length. One dimension might be the height, which is the product. And one might be the depth, or one might be the location, which is the depth of the cube. Now this is very limited, only using 3 dimensions. Cube is a misnomer. It's actually a hypercube. So it's something very messy like this, but when you query from a data warehouse, you get back rows and columns, so it looks like a table still. Now, OLAP and data warehouses are used for batch processing, not ad hoc or transactional use. So they're optimized for low latency reads, meaning selects, not updates. inserts and deletes. Now, humans and systems do not write ad hoc into a system like what we do with RDBMS. Instead, data is typically loaded in from another system via something called an ETL job. What happens is overnight, a bunch of queries are run, maybe on a production server or a clone of a production server, and that data is extracted. It's transformed somehow, maybe by doing group bys, maybe by joining stuff together, maybe by converting JSON into a tabular format, or vice versa. Something's done with the data. And then the results of that are loaded into a data warehouse. This typically happens overnight while people are sleeping, so that there's no downtime in the production or in, even better, the backup production server. This is the typical schedule of writes. So these shaded areas here are writes. With OLTP, writes happen all day long. With database or with data warehouses and OLAP, writes typically happen overnight. We do not write or update data in a data warehouse ourselves. Some script or system does it for us. What this means is, like, let's say you're putting together a report. What this means is that your data is going to be out of date, usually by a day. And that's okay. That actually helps you and your sanity. If you were to write a report or create a report using the production database, you're going to have to refresh that report every time you come back from a break to get updated information. Or you could filter it, of course. But still, it's not ideal. With a data warehouse, you have all day basically to write that report. And it's very easy to subset just to the days that you're interested in. As an analyst, you don't have to worry about data that happened an hour ago. You only are typically worrying about data from a day ago, maybe even a quarter ago, depending on, like finances quarterly. So to get data from a production database, or really any system, into a data warehouse or any other system, you use something called the ETL job. It's just an edge between two systems that I basically just described. You extract from this machine. You do some transformation, maybe on another machine in the cloud or something, and then you write the data or load the data into the right-hand side here, which is the data warehouse. Now, the ETL job either transfers all of the data or only the data since the last update. So for example, where I work, because some of the data can be modified in the past, we have to reload our data warehouse every night, even though it's usually the same data over and over. Other systems, a saner way to do it is just update as you go. If you know you're not going to update past historical data, just update as you go. So each day you're importing 1 day worth of data. Now you may lose some data if there's a race condition and inserts and updates are happening during the transfer. You may lose that data, but typically in a data warehouse, you're worried about aggregates. So as long as the rows are missing at random, any estimates of averages, sums, and counts will be unbiased still. So this is usually okay. So another thing that a data warehouse does is when you import data into it, it computes a bunch of aggregates. Now sometimes these aggregates are just computed on the fly by the data warehouse. Other times, the user specifies what aggregates they want to compute and what dimensions they want to group by, essentially. When the data warehouse does it itself, you see it's very computationally expensive. If you have n dimensions, n possible factors or in different groups, you're basically going to end up with 2 to the n processing time in order to compute all the aggregates on all subsets of groups. So for example, 5 dimensions A, B, C, D, or groups A, B, C, D, I'm going to compute an aggregate for A, B, C, and D, AB, AC, AD, BC, BD, CD, ABC, ABD, BCD, and ABCD. I think I got all those. I have to do this a lot. But aggregates aren't the only thing that data warehouses do. But because we have such fast aggregation capability, we can quickly access data in order to do things like reporting and dashboarding. The other thing a dashboard is used for is for denormalized or exploded tables. We have a context where we have to have a table that's joined, and we have to constantly do this join. Or at least we want to read this join data every day. So what we do is we just tell in the schema that we want to join these 2 tables together, and we store the result of that join. Now we can read it many, many times. As many times we can do it until we're blue in the face. It does not incur any extra time. We don't have to actually do the join. We just read the results of it. So that's great. So the big difference between OLAP and OLTP, OLAP cubes take a really long time to process, usually overnight. Reading aggregates or joins, denormalized tables, very fast. It's great. It's usually a select star. But your data is likely to be out of date, typically not a big deal. Typically append only, you don't append any data to the data warehouse. You only read it. Typically it's read only as well. There are 5 operators in OLAP that have now been implemented in RDBMS or OLTP. Slice, dice, roll up, drill down, and pivot. Slice, if we use this cube nomenclature, slice is like a loaf of bread, although a loaf of bread is a rectangle, a prism, whatever. If you slice that cube, you get back a single square, a square with some depth to it, or a piece of bread. Produces a rectangle. Slicing selects one predominant dimension on equality from the data. So here I'm selecting wireless mice. I only want information about wireless mouse. What is the SQL construct equivalent to a slice? Select what? Where? In particular, where equals. Dice, oh boy. So dice is, you're no longer extracting a slice out of the cube. You're extracting a subcube or a prism out of this other prism, essentially. This terminology typically is not used very much. We talk a lot about slicing and dicing data. We typically don't distinguish much between slice and dice. We usually just use the word slice. So a dice basically means we're selecting multiple dimensions or multiple values on multiple dimensions typically. So, location is North America, so Canada, US, Mexico. Product is Nokia, Motorola, Ericsson, Sanyo. What year is this? So this forms a subcube. Now, in SQL, what is this equivalent to? It's equivalent to a where. Yeah, there's a lot of where and or less than, greater than, less than or equal to, greater than or equal to. So it's some subprism within this larger prism. And so slice and dice are used interchangeably, but if you forget what they mean, you think of the onion. Don't think of the onion during the final because you might cry or something. But slicing an onion, it's a sphere. You slice it, you get a circle, or a circle with a little bit of height, a little bit of a cylinder, basically. And then to dice, so you've done one. Chop, and you get a slice. To get a dice, you now chop in multiple directions, basically, on that slice, to get little pieces of onion that you can put into your chilaquiles or whatever it is that you're making. But usually dice and slice are used interchangeably in industry. Okay. Roll-up is interesting. A roll-up is cool. So usually we may have data that's hierarchical. Roll-up only works with hierarchical data. So that's dates and times. Geography, or spatial. And I'll even say org charts. I'm excited that I have another hierarchical one I can mention. So what we could do is say we have our sales data again, and I have some data for sales on 1/1/22, 1/2/22, 1/3/22, and I have some aggregates for those dates. Because again, typically in OLAP you're using dates. I can then roll up these statistics. So if it's a sum, I just sum over the days for that month to get a January 2022 aggregate, just by summing up. So the average is going to be a little more complicated, obviously. I don't know how it's implemented. Average might just sum up across the days and then divide by the count. It might average the averages. I don't know, but presumably it does the right thing. I also have, let's say, 1/1/1970. 1/2/1970, 1/3/1970. So here I have January 2022 aggregates, Here I have January 1970 aggregates. I can then roll up even more and create aggregates for each quarter. So Q1 22, Q1 70, 1970. And then I can roll up all the way to a global aggregate. So a total number of sales across the entire company for all time that the company existed. This also works for other hierarchical attributes like geography. So you have city within county, within state, within a country. Or an org chart, which I had to do before. So for example, you might have a statistic computed within a team, number of lines of code written, I don't know. And then you roll that up to the manager level, then to the director level, all the way up to the CEO level. That's a roll up. What's cool is that MySQL, which is not OLAP but OLTP, can actually do this for you. It computes the entire hierarchy for you. Let's say we have data that looks like this. It's hourly sales for a variety of dates for a variety of years. We can write a simple SQL query to roll up this data. The first part looks very familiar to you. It's a select sum and a group by, of course. But what we group by is a roll-up, and we specify the levels of the roll-up we want to use. So the year is the highest. Then we also want to roll up by month and day. Now, if I want to skip a level in the hierarchy, I can do that. Just don't include that in the roll-up call. Now, what does this get me? Does you have a question? And a what? Oh, so a window function is usually used for a rolling window or a sliding window. So a window function doesn't traverse a hierarchy. The window function computes an average over some neighborhood of rows on a rolling basis. I know it uses roll here as well, but this is going up a hierarchy. So it's kind of two different dimensions, so to speak. A window function rolls along one axis, like time. This one, we're just going up a level in the hierarchy. So the y-axis, basically, versus the x-axis. So what does this give us? Then maybe this will solidify it. I have each day, I have April 21st, all the way through December 31st for 2020, whatever. And I have the total of all the sales. So remember, the data was hourly original. Now I sum up across the 24 hours or the business day or whatever. I have that. Next, I have monthly aggregates. But if I have a monthly aggregate, what do I put for the year? I'm sorry, for the day. Null. So I have aggregates for April and December of 2020. Then finally, I have an aggregate for all of 2020. And then finally, I have a total aggregate, all sales. Now, somebody asked if you were to materialize this result set, how would you query it? For example, to get the global aggregate, well, you're just gonna have to do select where year is null, month is null, and day is null, which is unfortunate, but it lets you do it. So, are there any questions on what a roll-up does? This basically gives you quick aggregates at multiple levels of a hierarchy. You could do it by county. You could then do it by city, and then by county, and then by state, etc. Okay. Drill down is the complete opposite. Now, there's not really a SQL option for this one. Basically, you take your roll up and you just query individual hierarchy levels to get a drill down. That's basically it. You're going from the global aggregate down to the day or the hour. So this is a little dashboard. This is kind of relevant to what I did at Facebook. We did create a dashboard for that was backed by Vertica, which is a data warehouse. And we were doing some sentiment on different kinds of page campaigns for large clients. The large client logo appears in the top right. There's multiple large clients like Walmart, Coca-Cola, and a variety of others. They can query particular days, and the data changes as they change the date. I can click on a state. All the data here will change for that state, and then the map will change to a county map, for example. And I can keep clicking, and my whole dashboard will change and reorganize itself in order to show me information about the particular category I'm looking at. So looking at this dashboard, where is the slice? Walmart. When we look at Walmart, we don't care about Coca-Cola. When we look at Coca-Cola, we don't care about anybody else. So that's the slice. What is clicking on a state? Anybody else? I click on a state, the map then changes to the counties in that state. Drill down. Yeah, good. I click on the man or the woman. What is that? Dice, yes. Okay, where is the roll up? No. It's hard to say. Zoom out one level is the roll up. Now, the roll up is actually data. It's actually a result set. Typically, this is called a drill up. This operation of clicking that button is typically called a drill up, but it accesses a roll up table to do so. So we kind of distinguish the two a little bit. But if you were to say roll up here, it's correct, basically. We don't need to get pedantic. So any questions? Okay. Pivot, we already talked about, lecture 4. So if you don't understand pivot, take a look at that one. But pivot is the 5th operation, and it can't really be represented as in a dashboard. However, you're taking an R class, and I don't know if in this R class, are you using ggplot2? Okay, so in order to create graphics in ggplot2, where you have different categories and different color bars to represent different, I don't know if they're going this in depth with it, but you could have a bar chart, and then you can have a bar chart with multiple categories, so you have 2 bars of different colors. In order to do that, you have to use pivoting. It's really frustrating, but you have to use pivoting to do that. So you're constantly converting between the wide and the long format in order to analyze your data and then plot your data. I believe ggplot2 wants the long format for plotting, where typically you use the wide format for analysis. Okay, any questions on pivot? As always, we're going to finish early, but that means I get to talk more about the exam. The same that I told the last section, obviously. All right, so some examples of data warehouses. Vertica is a pretty common example. I don't believe you could classify it as anything but. Let's see. Let me actually pause on this slide. Can I add? Okay. Okay. I count in 3s. And you're all kind of partitioned in 3s, which is kind of funny. So let's do this one last time. Last time. I wish I could count in 10s. It'd be so much easier. Hive is a relational layer on top of a distributed file system. It's sometimes called a database. It really isn't. But we do sometimes call it a data warehouse. So at Facebook, Hive was called a data warehouse. Oracle has a data warehousing product. I don't know if it's the same product as their databases product. SAP also is another good example of a data warehouse. Presumably Salesforce may also be. Anyway, on the cloud, there's a few different ones. They're hard. Google Cloud is hard to describe with this one, but I'm going to say BigQuery is a data warehouse. I think they also call it a data warehouse. Sometimes it's also just referred to as a database. Redshift on AWS is a data warehouse. So is Synapse on Azure. Never used Azure, so as LeVar Burton says, you don't have to take my word for it. Summary of OLAP. So OLAP is optimized for fast access to aggregated data and joined data, not individual rows or transactions. The data is multidimensional and represented as a cube or a hypercube, not as a table. However, when you interact with the data, it darn feels like you're working with a table. But data is loaded in bulk, not row by row. Again, it's not transactional. So it's loaded by an ETL job overnight, usually. There's reduced reliance on the relational model and schema design. So, reduced reliance on joins. You don't have to join data together. So you can, but you don't have to usually. And it's very, very fast. No online modifications. Many of the OLAP concepts, though, also apply to databases in OLTP. Now, I want to end the course content on a couple things here. In this career, there's a lot of hype. And you have to really learn to filter the hype and the BS from the real stuff. 10 years ago, the data scientist role was a ton of hype. There's still some of it. People want to get into it. That's great. That's not hype. That's good. Hype is like saying it's like the highest paid profession ever, which is not true. And a bunch of other stuff. Calling it the sexiest job alive. Well, I've heard many jobs called that. There's a lot of hype behind it. Right now, we are in a big AI hype. I hate that we call machine learning AI. There's technically the difference. AI is more classical, first order, propositional logic, stuff like that. But there's a lot of hype about it right now. And, things like, is ChatGPT or LLMs going to replace data scientists? No. It's going to make our jobs easier and maybe shift what we do, but it's not going to eliminate us. Is it going to replace software engineers? That's a stupid one. Who built the LLM? Who built the tooling for the LLM? So probably not. It may reduce the scope a bit. Will it kill Stack Overflow? Now that's a more interesting question. Or search engines or whatever. I hope not, because where do these LLMs get their data? So if Stack Overflow dies because of ChatGPT or LLMs are screwed, basically. So I don't think that's going to happen. But when I talk about hype, that's kind of what I mean is a lot of these doomsday predictions. So if you've heard them, don't worry about them. If ChatGPT is going to replace all of us, it's not going to be for at least 20 years, if even that. So you'll have plenty of time to find another job. But I highly doubt it's going to come to that. Data lakes is another thing that was a big hype driver about 2-3 years ago, around 2020ish, and it still is. So I want to talk a little bit about that. It is a real concept, but a lot of marketing hype. And I'll go through this relatively quickly so we can talk about the exam. This is from near my house in Mammoth Lakes. It's some lake, I don't remember the name of it, from the top of the mountain. If you're new to, I hope everything's okay. If you're new to California, I encourage you to go to Yosemite and or the Eastern Sierra. Mammoth is pretty close. It's about 5 hours away. There's skiing, mountain biking, all that stuff up there. Anyway, up to this point, we talked about OLAP and OLTP, and you may have heard about something called a data lake. And a data lake is referred to a particular architecture where data is stored in multiple systems, so multiple machines. It's distributed. And in many different formats. So you just dump a bunch of data of any type into this data lake, and it's just supposed to work. So they're viewed as an alternative to data warehouses. So data warehouses still typically have a schema. It's kind of sort of relational, kind of sort of cube. Data lakes have no schema at all. You put anything you want. Anything your little heart can comprehend, you can put into a data lake. A data lake is basically a single system. So it has multiple nodes to it, but it's a single interface. And you put raw, unprocessed data here. This could be tabular data. It could be music, PDFs, audio, Word documents, whatever. Anything goes in there. There's no schema. How could there be a schema? And typically, the contents of a data lake are ingested by some machine that's dedicated to a particular use case. So processing a particular kind of data. Now, the way that I visualize this is like a water pump that pumps water out of a lake. It's going to pump up everything. Not only the water, but the fishing line, the algae, and all the dead fish, and everything else that's in the lake is going to be pumped into this pump or read by this node, the system. So data lake is basically a giant repository of data. It requires a lot of upkeep, and a ton of upkeep, because there's so much crap in these data lakes. And so critics note that data lakes blow with unnecessary data, because typically people just dump any data they can find. Doesn't matter how incomplete or bad it is, they dump it into the data lake and hope for the best. So sometimes people call these data swamps or data graveyards. The data goes there to die. Nobody's ever going to read it again, but we think we might need it, so we just put it into the data lake. Okay, so this is how I envision a data lake. It's not clean, it's very messy, it's very not useful. My boat will get stuck in this. The water is not useful to me because there's so much junk in it. So this is how I envision a data lake. Okay. Now, as academics, there is a concept to be respected here. Academics meaning researchers. Because these are such a mess, is there a way that we can create a system that processes data efficiently from a data lake, given that there's no schema and no theory? It needs to be programming language agnostic and a bunch of stuff, and we need to be able to index it efficiently. So those are open research problems if you ever decide to get a PhD. I don't regret mine because I can teach, but God, I never want to go through that again. And so a lot of companies offer data lake type stuff. Typically they're used for something else. They're not designed as data lakes, but they wanted to join the market hype and the market train and said, hey, we have something that's basically a data lake. Now, Amazon is probably a good example here. They have something called S3, Simple Storage Service. It's not really a file system, but it's a place where you can dump a bunch of data. So to me, S3 is a data lake. That's a fancy name for it. Data lake, it sounds a lot more fun than it is. Cloud storage, Atlas data lake, etc. The most successful data lake, though I argue, is the Hadoop distributed file system, or just distributed file system. When you run a MapReduce job or Spark or whatever, you're typically running on the distributed file system, and you can put whatever you want in there. There is some order and some organization to it, which is good, called directories typically, but it's probably the best example, and I hope this is what we agree on. I'm going to call it the best data lake. So let's just focus on building this out. Now, the hype has continued into something called a lake house. So now you have your data lake, now you have a little house that sits on the lake, where you, I guess, control the lake. So presumably a lake house, I haven't researched this, is probably some kind of node that kind of oversees the data lake and does processing within it. It's just, how long are we going to go with this data lake analogy? Yeah. We have warehouses, we have databases. Do we really need a data lake? Are we going to have data caves, data mountains? I don't know. So HDFS, if you don't remember or don't know, is a distributed file system that powers Hadoop MapReduce, which is old, and also Apache Spark. So I hope you have a class in this program that teaches you Spark or something like it. So that's important to know. You may not use Spark in your job, but understanding MapReduce and distributed processing is pretty important, I think. This is kind of, when we talk about data lakes, it all gets wrapped up into these variety of layers. This is the Hadoop and Spark ecosystems. So down here, we have data buses. A data bus is basically just somewhere where you get data, where the data originates into your hands. So it could be a real-time stream, it could be files, anything like that. You then take that data and throw it into a file system where you can now use it. That file system is managed usually by an orchestrator or a cluster. Actually, this is the orchestrator out here. Some cluster manager. And Hadoop MapReduce, Spark MapReduce, interacts with this cluster manager in order to determine where data is, where the finished files are, and all that fun stuff. Stuff that you don't have to worry about. You're going to be up here for most of the time. Hive, maybe here, maybe HBase, maybe even Cassandra, I don't know. This top layer though, this is you using data. So Pig uses relational algebra operators as a scripting language. Hive is like a data warehouse kind of. It's a relational layer on top of a distributed file system. So you're mostly going to be up here. But it helps to understand some of the lower stuff as well. The lower you get, the more of an engineer you become, essentially. Right. So you may see these things and wonder what they are. They're not all the same level. There's various levels to this kind of architecture. Okay, are there any questions about OLAP, data warehousing, data lakes? So now you don't have to buy into the hype. You understand what it is. It's nothing that special. And if you create a data lake, don't try to sell it to me. I don't want to hear it. So we've ended the material for the class. Now we're going to talk about the final exam and a couple of parting words. So congratulations on that. The final exam is this Thursday. I know there are some questions about this. It's this Thursday, November 2nd, from 1 to 4 or 4 to 7. For you all, it's 4 to 7. In gold, B117. So if you're not familiar where that is yet, it's in the basement of B. You go into B, take the elevator down to the first floor. It's a really sad place. It's one of the only places that has a bathroom but doesn't require a key or a code. So it's down there. That's where I had my class last year. So it'll be in there. The exam, I'm going to try to write a 2-hour exam. Doesn't usually work out, but I'll try. You'll have the whole 3 hours to complete it. There's some question about policy here. Because typically every class has to have a 3-hour exam. Or at least I have to give you 3 hours to complete it. So, there's a lot of material. By saying I'm giving you a 2-hour exam, hopefully it's 1 for people who are really on top of things and just multiply by 2 for everyone else. I don't know. We'll see how it goes. Your session may start a little bit late. So technically we start at 4:10. Depending on what happens with the previous section, how quick I can kick them out and sign them out, there may be a little bit of a delay starting, but you'll have the full 3 hours to take the exam. So just please wait outside until we let you in. You need to bring your Bruin card. Hopefully you have one. We're going to be checking them either at the beginning or the end or during or all three. I don't know. Both sections will have entirely different exams. However, they'll be equivalent but different. However, no part of the exam leaves the room, period. I'm serious about that. You need a reliable laptop. So if you do not have one, you're going to need to get one. This includes, so there was one person on the survey that said they didn't have a reliable laptop. So that person, if they can, I'll figure out who it is and write to them. But at UCLA, you can rent a laptop through Powell Library. So I suggest doing that today or tomorrow. You can rent it out for a week. There's a self-service option. It comes with all kinds of software, very easy to use, and you can keep it for a week. And it comes with a charger. So just use that. If you have a laptop that you use, but you're worried that you may not find a power outlet, very valid concern at UCLA. You may also want to rent a laptop. So I'm talking about laptops that have bad batteries, like mine. So I recommend that. You cannot take the exam without a laptop, though. If you show up here without a laptop, you're going to have to run and check out a laptop and hope they have some left. You cannot take the exam without a laptop, so do not wait until Thursday, 5 minutes before the exam, to go to Powell to get a laptop. We will not give you extra time. So yeah, that. So I've hemmed and hawed a lot about what to do here. I have decided not to use Respondus because I spent all weekend creating this beautiful little website for you that had all the resources. I spent all this time trying to find a web-based terminal. Respondus doesn't like any of it. You cannot right-click in Respondus. Like all of these things I should be able to enable for you, and I can't. It's a one-size-fits-all thing that's extremely annoying. So we're not going to use it. I have to, trade off test security with sanity. And I want you to be able to use your computer to some extent. However, this does mean, and I know you're gonna be annoyed with this, I'm gonna ask you to print the materials that you need for your notes. Because on your screen, there should only be a terminal or the final exam, nothing else, and we will be checking. So in order to do that, we have to really reduce how much we allow you to look at things. So we're gonna ask you to print, you have a quota to print, I've heard it's plenty for this class. Print any slides you might need, which means don't print all of them. You can if you want, but I don't recommend it. Print homeworks or textbooks chapters you might need. If you want a cheat sheet too, yeah, I mean, you can. It doesn't have to be printed, but it cannot be on your computer. Your notes have to be physical. We have to be able to see them. You can use the class MySQL server using your terminal. We're not going to use the web-based thing. Weird stuff has been happening with that. Again, the only apps you can have open are the terminal and the final exam. The campus wire will be deactivated, but you shouldn't be accessing it anyway. If you need scratch paper, you can ask us, we'll have it, but you have to give it to us when you sign out for the exam. Nothing leaves the room. So the point of this class is to learn the syntax of SQL. There's actually various reasons why I can't allow data grep to be used for the exam. One of them, the one that I'll tell you, is that it defeats the purpose of understanding the syntax. So, use the terminal, use the box that's on the final exam to write your query, and then copy and paste it into the terminal to test it. And then when you finally get an answer, wrap it up in the box. You must comment any English that's in the box, because we're gonna run these automated, just like we did with homework 1. And like 70% of the class didn't follow directions and got a nasty gram that your code didn't run. It's because we did it in an automated way, and we ended up having to manually grade a lot. Again, only things on the screen are your exam and the terminal. You may not use any other applications during the test. I will be walking around and checking. It's a 0 if we find it. No communication, nothing. This is 0. Bring a pen. You're going to be asked to either sign in or sign out or both. If you don't sign in or sign out or whatever we do, we're going to assume you're not in the class with everybody else taking the exam, which is a 0. 45% of your grade. The format is true, false, multiple choice, fill in the blank, some explain type questions like on the homework, and then queries. I don't know what by the way, all of this is going to be posted as well. I always withhold this section of the slides so that everybody listens or takes notes. And then after the class, I will post everything onto Brew and Learn. So you can see it there as well, but you can take pictures too. Queries are probably half of the exam, maybe 4. On the 4 like standard queries, and maybe 1 or 2 quick queries like updates or something. I'll see. I don't know. I have to look at last year's exam. The difficulty of the items are going to vary. The grade cutoff is not going to be based on the average. So it's not average gets a B or an A- or anything like that. It's based on how the class does overall and my judgment of expectations. Again, you're graded as a grad student, which means A, B, C. F if you don't do anything or don't show up to the exam. A and B is passing, C is not passing for credit. The program has a recommended curve. I didn't put it in here. I haven't followed it. I think it's something like at least 5% a C+, which is not passing. At least 5% a B-, which is also not really passing. I don't believe in ranking people and failing the bottom 10%. It's based on my expectation. So, some tips. I'll let you read these tips. Make it count. It's your last opportunity to show us what you know. Trust yourself. If you're unsure, write what you know. It's either right or it's wrong, but it might be right. So write it down. Prioritize your time by point value. Sometimes people, last year, I had somebody who left all of the SQL queries blank, which is like over 50% of the exam, because they spent all their time on 1-point multiple choice questions. Ouch. Don't do that, please. Again, the rules for writing queries. Again, the point here is to show the breadth of your basic SQL knowledge. Last year, I had some people write window functions for every query, and we really had to penalize them because they didn't show us that they understood base constructs like group by or how to write a very basic select from where. They immediately went to the most complicated thing. I'm gonna be a bit more explicit. If I want you to write a window function, I'll tell you to write a window function. If I don't specify that, write a regular SQL query. Same thing with recursive queries, if I ask that. I'll have an office hour or 2 office hours on November 1st, which is 3 to 5 p.m. on Wednesday. Now, I cannot submit grades until the first week in December. I can't. That's just the registrar's thing. So your grade will be posted on Brew and Learn, and the grade is final. There's no arguing for points. The grade's final once it's posted on Brew and Learn. And then the same grade will be posted on my UCLA and your transcript in early December. You can review your exam with me if you want after the grade is assigned. So this is final. So basically everything that was covered in the class is on the exam in some way. So let's go through the list, including but not limited to, just in case I forgot something. Database models. So this is, you should understand relational ER, object-oriented graph and document. When are they used? What are they good for? What are they not good for? You should understand keys, various aspects of them. What is a super key? What is a candidate key? What is a primary key? And what is a foreign key? Relational algebra. I'm not going to ask you to write a full expression, but you will see these symbols, so know what they are, know what these cute little symbols mean, and what they do, and how to translate from SQL and back. Data type and schema. Understand how to create a schema. Understand constraints and data types. So this is stuff you should put like a cheat sheet or have very close to you. How to change schemas and why you should not change schemas. Basic SQL, extremely important. Select from, where, group by having, order by limit. Offset we didn't talk about this year. It's mainly used in web apps. You should assume that something is a select query unless I've told you to change something in the database. Okay. All right, what else here? Let's use red. It looks like a laser. Data management. You should understand the basics of insert, update, and delete. I'm not going to harp a lot on this because you're not going to use it a whole lot. So maybe one question on those each. Joins. We talked about inner, outer, self, equa, non-equa, semi, anti. For outer joins, we talked about left, right, and full. Guess what? Full is not implemented in my SQL, so I'm probably not going to ask you about it. It's really important that you get the join type right here. Yes, you can write an inner join as a left join. It's a left join with an is not null condition in the where. You will not get full credit for that though. We want to know that you understand what an inner join is and what the syntax is for that. So please don't use left join everywhere or full join everywhere or window functions everywhere. Subqueries, derived table, scalar, and what's bad about correlated subqueries and when they're not bad. How to write a window function. I might ask you to write one from scratch. I might ask you to fill in the blanks. And maybe some of the blanks aren't filled in, depending on the problem. Same thing with recursive SQL. You should also know other SQL constructs like case, cast, coalesce, like, and the JSON operator. That's page 1. Page 2, you should understand the OLAP operations and what the point of OLAP is, what an ETL job is, what the ET and L mean, what a pivot is. I usually don't ask you to implement it, it's complicated, but you should understand the 2 formats, the long format and the wide format, and when to use which one. You should understand the difference between OLAP and OLTP, when to use which. This one we didn't talk about this year, so we can get rid of that one. We don't need to study something we didn't learn. Oh, no problem. I think you'll talk about it in 405. I talked about it last year, but MySQL's query plans aren't incredibly interesting. Functional dependencies, how to identify them using the axioms. And then finally, normalization. Classifying tables into 3NF and BCNF, decomposing to BCNF, either via your intuition or by using functional dependencies. And then finally, the concept of losslessness. Let's get rid of dependency preservation. So are there any questions on what's on the exam versus what is not on the exam? Everything's on the exam, yeah. Mhm.
Will we get access to last year's midterm?
No. The homework should be used as your practice for the final. Mm-hmm. I won't completely rule it out. It's unlikely. It depends. I always write a completely new exam, but it depends. If I end up finding that this year's exam is very different than last year's, then I might release last year's. Just don't count on it. Mm-hmm. Yeah.
Your office hours during our stats midterm, so is it possible for you to go to the office?
Yeah, somebody really needs to give me a list of everything that conflicts. I really need to have access to that, and I've asked and not received it. Yeah, I'll find some other time for it. What else? Yeah.
How's the typical course? Is it like equivalent to what we have like for homework?
No, the homework is way tougher than the exam. Way tougher than the exam. Because you have a week to do it, or 5 days to do it. Mm-hmm.
Wait, how many questions on the exam? Like that?
I don't remember. I think last year there were 25 or 30 multiple choice, true and false type problems, and 4 or 5 queries. So something like that. Any other questions on the content of the exam? And then we have a couple more slides. Yeah.
Are the questions multiple answers?
I can't hear your question.
Are the questions multiple choice answer questions or other?
There are multiple choice questions. There are free response questions as well. Mm-hmm.
Will you ask us to write a recursive query?
Not from scratch, I won't. If I ask you to write a recursive query, it'll either be I give you blanks and you fill them in, or I ask you a question about the steps involved in it. Yeah.
Where should this document on the
Yes, it'll be on Brew and Learn. Any yes.
Well, concepts like data lake also included in
Data what?
like data lake.
There's not a whole lot I could ask about that. I mean, you should know what it is. What's in the slides. Mm-hmm.
We won't have access to Brew and Learn during the exam.
You'll have access to the final exam on Brew and Learn, but any notes you use, you need to print out. Yeah.
So on the final exam, can I just open the text editor on my computer instead of using the...
Use the box that's in the final exam. Mm-hmm.
Can we only have printed notes or can you use handwritten notes?
Handwritten's fine. Just nothing on the computer. Anything else? Yeah.
How many pages of notes we can print?
As much as you want. As much as your heart desires. If you want to print out all the slides, that's fine. Typically, those students don't do as well. There's no restriction. Typically, people that print out everything don't do as well. Unless they're doing it as a backup. But if they're doing it because they don't understand the material, that's not good. Anything? Uh-huh. Well, the due date is the final exam. Is Wednesday. I think I may have given you extra days. Last year I gave the solutions out. I might do that again, or ask during office hours. Any other questions? Yes. Yeah, you can print them. You can print any notes. Oh, I'll enable that. Any other questions? So we have a few more slides after we finish this discussion. Yeah.
Can we bring a book?
It's open book. So yes. If you have a printed copy of the textbook, you could bring that with you. Anything else? Okay. Let's finish off then with a few other logistics. Apparently there's a summer project and or internship, and I didn't know this last year, so I was quite caught off guard when I got a bunch of emails about this, and I basically had to tell a bunch of students no, because I have no idea what this is. Now I understand what it is. So apparently you either have to do an internship or some research or some kind of project over the summer in order to graduate or something like that. Now, I'm not a research professor, so I don't have a research lab, and I don't have funding to do that either. So that option I can't do. However, if you want to work with me and you have a project in mind you want to work on, I'm happy to work with you. It doesn't have to be related to 402. It doesn't have to be related to SQL. It could be anything. If it's machine learning, data science, stats, whatever it might be, if you have an idea for a project and you want to work with me, feel free to reach out. I'm happy to do that. Now that I know about that, I can offer that. I just don't have any research or internships to offer, but I can definitely help you with a project. Okay, moving on. So we have 10 minutes, so I can get through this. So again, I said this in lecture 1. Focus on the job description, not the job title. Throughout my career, I've made several mistakes where I picked a job based on the job title. It was data scientist or machine learning engineer. And then just thought, well, once I get there, I can kind of change the description. It's never worked. So currently, I'm a software engineer now after being a data scientist. I wasn't happy with what the description said of the job. Take it seriously. What's in the description is what you're going to do. Now, sometimes companies change the description to be a lot more boring than you want it to. Well, then that's when you need to change your job, essentially. But always focus on the job description. At any entry-level position, focus on positions where you can learn as much as you can. Now, I didn't tell the last class this, and I meant to, we were rushing. I once lost a return offer for a contract, essentially, because I could not write SQL. This was before I learned in-depth SQL. I learned a lot of relational algebra, but not SQL. So for those of you who struggle through this class, my heart's with you. Don't take it personally. It's 5 weeks. This is a lot of material. And some of you haven't figured it out yet, and that's okay. I didn't figure it out. I had a master's degree in CS, and a bachelor's degree in stats, and a master's in stats. And I could not figure out SQL for the life of me at that job. I took it as a wake-up call, though. Then I bought this book. What's it called? The Joy of SQL, I think? Something like that. It's a little thin book. It's in lecture 1 slides, and read it. 5 months later, I ended up at Facebook, and I was the team expert at SQL. Now I teach a class in SQL and also in databases, and it's become my academic research area. So it doesn't matter what grade you get in this class, or how much you struggled, or how much you just hated this class. You will be fine. Just keep working at it. And believe me, you will become very good at it. And even if not, you'll be useful at whatever else you learn. And you'll find your place within the industry. So I promise you that. Just keep working hard. SQL is very important, as I mentioned, so I got ahead of myself here. Some of you are going to spend all of your day for the rest of your lives, or the rest of your times in your career, writing SQL. Some of you are only going to use it maybe once a month. That's me. I only use it maybe once a month for my job. And even as a data scientist, I use it even less, believe it or not. It really depends on the company and the role that you're hired to do. So again, if you struggle with SQL, you may get lucky and end up somewhere where you don't have to do very much of it. And that's okay, it's just as valid. Finally, if my door is always open, virtually obviously, if I could be of any further help after this course ends, I don't care what it's about, if it's related to 402 or not, feel free to email me. I'm always checking my email. I'm always happy to hear from students regarding what you're up to, or what your any questions you may have, whether it's academic or related to industry, or just want to say hi. And finally, thank you for a great 5 weeks. I know this is a very, very tough thing to study in 5 weeks. So thank you for your hard work and your patience and dedication to learning this important topic. So thank you. Thanks. Now for the last time, where is the sign-in sheet?